Well, thank you very much. It's a great pleasure to be here. I think it's my first talk in front of a real audience. It's like 2 years, so thank you also for being here. So I'm been invited to present a little bit of my research. So first of all, I would like to say that what I'm going to present has been in collaboration with some long-time collaborators. So we are now scattered across North America, in the US, Mexico, but also in Europe. So all you're going to see was been developed with those gentlemen and ladies. So in the history of physics, we've been going deeper and deeper inside molecules, then atoms, then protons, and nowadays, finally, well, it's believed that the elementary particles, as of today, are called quarks. So quarks are, well, a proton, a neutron are composed into 3 quarks. So experimentally, we've been going deeper and deeper. But of course, what we would like to understand also is how from the previous constituent emerges the, the next one. So like from protons, how they interact and form nucleus, or as quarks, how they interact and form neutrons. So there is the experimental side when we go deeper and deeper, but we also want to go to the understanding in the other way, from a theory, how we go to understanding how these new degrees of freedom emerges. So at the level of the quarks, so we know now, we know fairly well the interaction between the quarks. We know that they interact through what we call gluons. And we know the basic equation or Lagrangian that govern this interaction. Unfortunately, this is still very difficult to solve in practice. So it's possible to discretize this, plug it into a computer, solve the equation, and trying to extract the properties of the emerging resonances or bound state. That's one way of doing that, is to start from a theory, like the quantum chromodynamics, and then make predictions. So as I said, so solving this equation, making effective field theory based on symmetry, for instance, and then trying to make prediction to explain the data and see whether there is an agreement or not, if we understand the properties of these new emergent degrees of freedom. So this is called the top-down approach, is when you start from the theory, making prediction, compare with data. What I'm going to explain, and this is done by my colleagues, by also colleagues here in the audience, and this institute. Another approach is, which I'm going to explain here, it's more focused on the data, the bottom up, when you start from the data, trying to have some only very generic principle, and trying to understand the content of the data, how this resonance and bound state emerges. So as I said, so what we think is the elementary constituent are the quarks. So nowadays we have like 6 quarks. We know, so the light quark, up, down, and strange, and then some more heavy quarks. So this quark can be bound into 3 triplets to form baryons. So most of the ordinary matter are composed into baryons. So the proton, stable, the neutrons, almost stable under certain conditions. But then you can have also different combination of quarks. So you can have baryon lambda, which is a U, a D, and an S quark. This quark can also be bound into pair of particle and antiparticle, like a quark and antiquark. The standard one that you may have heard are the pion, pi, the kaon, and then one that we will talk later is called the J psi. It's a very important particle in the history of particle physics. But the theory, so those are fairly well known. But the theory predicts that there may be also other type of configuration of quarks that may or may not be present in the nature. So this type of configuration are called more exotic because they don't fall into the natural pattern that we know from decades. You can have like what we call hybrid mesons when the gluonic field is an excited state, and then that can bring quantum numbers, we'll see. You can have like more configuration of quarks, so you can have like 4 or even 5, so they're called tetra or pentaquark. Or you can have even states with no quark at all, glue balls. So the question is whether those play a role in nuclear reaction or not? Do we need to consider that when we want to describe a reaction between particles like pions, protons? So in this talk, I won't talk about all of them. I will just give like 2 examples of data analysis on this state. But before doing that, we need to work on, we're going to explain a little bit about the vocabulary, what we call a resonances, a bound state. We'll take the deuteron as an example to see that. So that will be useful. So I said that the baryons, the 3 quarks, they can be 3 different types of quarks. I'm going to take the example of these baryons with 3 U quarks, and we call delta. That's his name. So this guy can decay. So, and it's actually produced when we take a pion, which is like fairly stable for us, so we can make beam out of pions. So we can smash a pion against a proton. And then if you look at the quark content, it's clear that the D quark of the proton can be eaten or can annihilate with the D bar quark of the pion. And then those guys forms like, we have 3 U state, 3 U quarks, form a resonance. So in terms of the data, what do we see in the data? When this particle, when we smash that together around the mass of this guy, it's like having like an attractive potential somehow, and having like not a bound state, but a resonance. So in terms of the data, if you look, So if you look at the data, if you look at the wave function of the pion-proton system, you have the imaginary part here, and you have the real part here. So if you're familiar with complex variable analysis, then you will realize that when you see like the real part that changes sign and then a peak for the imaginary part, you can see it's a pole. It's actually a pole. So the theory, the relativistic scattering theory tells you that when you smash 2 particles, actually the wave function is a complex function, and there's like a cut on the data, on the real axis. So here, this is the real axis. I don't know if you see very well, but here it's a representation of the imaginary part. So you have the data in red, which is this thing. And you know that, so the theory tells you that because of causality, you have a cut. So this is, now I told you that the resonances is what we call like a pole. So where is that pole? Here, there's no pole here. But you know that there is a cut. You have like a second Riemann sheet, which is smoothly connected to this one. So if you look at what's in the second Riemann sheet, smoothly connected to this one, you can see that here you have a pole. So this diverges here. So this is what we look for. So this is the property that we look for from the data. What are the poles that create the enhancement on the real axis here, which are the data here? So the first thing to see is that in order to extract the properties, you cannot just use the data, because the data is just on the real axis. Well, you need to go somewhere in the complex plane. How do you do that just with the data? You need an underlying model. You need a model for the dynamics, very minimalistic possible, so that you need to go to the complex plane. So instead of representing this 3D plot, typically we would just put like this plot and then say, okay, this point here, it's like a pole in the complex plane, so under the Riemann sheet. Now, another example you might be more familiar with is the deuteron. So to explain bound states, well, we talked about resonances. So what are bound states? So if I take a proton and a neutron in the same spin state, you know that the potential is very attractive so that it can create bound states. We can have like a deuteron. So the deuteron is like a negative energy, right? So it's below threshold. So it's not here in the second Riemann sheet. It's like on the real axis here, on the physical sheet, the first sheet. See here. Another characteristic, because the potential is very attractive, you know that we have like a positive scattering length, right? Now imagine that, of course, the neutron has a spin 1/2. I can also flip the spin, and I cannot do that continuously. But if I could, I know that I'm going to reduce the strength of the potential. So the strength of the potential reduces, and then by doing that, the pole actually goes to the threshold and then go into the second Riemann sheet. And then this guy, so we have like what we call a virtual pole. So this is not a real particle. So when we have like proton, neutron, when in a spin singlet, we know that there's no real particle, there's no the equivalent of a deuteron in that case. The only difference in the data, I mean, there's pretty much, at this stage, there's almost pretty much no difference in the data, except that the scattering length is negative. So the data in the very close to threshold, we know that the data is really proportional to the square of the scattering length. So here we have also the same thing, the same problem, is that if we understand, if we want to know the nature of the pole, if it's like a real pole, like the deuteron or a virtual pole, we need a model to determine what's the sign of the scattering length. So this is not something we can do just with the data. That's what the point is. So now let's go back to our practical case. So first of all, the hybrid mesons. So how can we spot a hybrid meson? So I took this one because it's one of the easiest one to identify, because it can be identified just with the quantum numbers. So I say it's a QQ bar, it's a pair quark-antiquark with an excited state and then with an excited gluonic field. And this gluonic field may carry quantum numbers, so that's how we can spot it. Because if we take just a quark and an antiquark, they spin 1/2, right? So the spin 1/2, okay? So they spin 1/2, and then so the total spin can be 0 or 1, parallel or anti-parallel. The angular momentum determines the parity, and then the charge conjugation is just the combination of spin and angular momentum. So with this, if I have only a quark and an antiquark, I have only possible quantum numbers that are in blue here. So this one, this one, this one, this one. The one in red are forbidden. So if I see some quantum numbers, so if I see a resonance that I have quantum numbers like this, this, or that, I know it cannot be a QQ bar. It needs to be something else. So that's why it's maybe easier to look for exotic in certain specific quantum numbers, and we know that cannot be QQ bar. From theoretical calculation, we know that the expectation is that the lightest one has like 1 minus plus. It would be like this one, right? So the question is, how can we have like 1 minus plus? How can this guy can decay? What kind of decay we can observe? It's not difficult to see that we can take two pseudoscalars. So the pion is like a pseudoscalar. It has 0 minus plus. If I take another pseudoscalar, I form a 0 plus plus. So I need to put them in a p wave just to get 1 minus. I need 1 angular momentum. So the main decay mode of this one is called the pi one, because it's like a pion with an angular momentum of 1. It needs to decay into a pion and to what we call an eta. It's like the isoscalar, the isospin partner, the 0 isospin partner of the pion. So that's the main decay mode. So then that means that experimentally we're going to look for this state and see whether those guys are in the p wave, what's happening, if do we see something or not. So this has been recorded a decade ago by the COMPASS collaboration at CERN. It's the pre-injector of the LHC. And this is just the spectrum. So we see the eta pi, we see the eta prime pi, the eta prime, just the heavier version of the eta. And we see the spectrum here. But the spectrum does not tell you anything about the wave. If we want to know the wave, S wave, P wave, we need to know the angular distribution. So we need to split this data just to see the angular distribution. So this is the cosine here, and then the same mass here, right? So now we can see clearly what's happening. Here we see that we have like a spectrum which is fairly symmetric. This part is pretty much the same as this one, right? So if you see something symmetric, that means that there's pretty much only even waves, S wave, D wave, etc. That means very little odd wave, so very little exotic wave. The odd wave have exotic quantum numbers. So for dynamical reason, in the eta prime pi, it seems that just by looking at the data, very little exotic mesons. On the contrary, for the eta prime pi, we see a very strong asymmetry here, right? So the COMPASS data has analyzed this in terms of partial waves. So they do an expansion in angular momentum, and then they analyze the two channels, the eta prime in black and the eta pi in red. And then you see that the even wave So L equal 2, L equal 4 are pretty much the same when you rescale for phase space. So, but for the P wave, the one that we are interested, the eta is very small here, and this one is very big. And we can see that for the asymmetry, right? So the question is like, how do we reconcile that? Because in principle, if we do have like a resonance, it should contribute to everything. So this guy should contribute to both this one and this one, right? And then in the history, when this data was first published some time ago, or even before, there was a controversy because when you look at the data and the eta prime, you see that the peak is not really at the same position. So people at some point, they were claiming there were two exotic states, even though that there was no explanation of why it was like a 14 MeV here and a 16 MeV here. They were just saying, well, if you look at the data, it looks like there are two different things. But it was not really satisfactory. So we did like a couple channel analysis with some principle, general principle, the most general thing that satisfies some principle like analytic conservation of probability. And we found that this announcement can be explained only by one single exotic pole. If I can pause this slide, yes. So here, so this is again the complex plane, and here we see the pole here. 5 minutes, okay, wow, okay, so skip that. So there's new data coming, and there's, from last week, there's also new data on the isoscalar partner, but I have only 5 minutes, so. Now, quickly on the heavy sector. So the heavy sector, so I talked about the gypsy, the CC bar, and I said that, so it's two heavy quarks, so it's very easy to build a constituent model and see what would be the prediction of the state. What kind of quantum number can have like the CC bar, and those are in black. And those in black are predicted and discovered. Those in blue are not yet discovered for other reasons, but they are predicted. And then recently, in the last 15 years, there have been like a lot of states that are in red that we don't know what they are. And those one here, it's even in the charge sector. So this is even worse because those one, they are charged. So the CC bar, you see it's a neutral electrically. Those one are charged, but they decouple to CC bar. So those guys, if they really are true resonances, they need to have at least 4 quarks. So there are a lot of, every single state here would require like a whole talk. I'm gonna talk about, just briefly about an analysis about what's possible a pentaquark now. So this has been recently observed by the LHCb collaboration. When your lambda b decay into 3 particles, and then you look at the spectrum of the gypsy and the proton. So this is the gypsy proton math. Those are the data. You see what could be like some potential signal. So why it would be a pentaquark is because if you look at the quark content, if you want a gypsy and a proton, there's no way the C bar can be annihilated by one of these quarks, right? So if there is a true resonance, in this case, it would be like a 5 quark. So we did the same game with taking the data, trying to see whether there is like a resonance or not. Now in this case, what is really important to understand is that there is a threshold. There is like an opening of these baryons and these mesons that can happen. So that means that this particle, most likely, if there is something here, this decays into the gypsy. This is the gypsy proton channel. But if I remove the gypsy proton channel, if I decouple that guy would be either a bond state or either a virtual state. So if you look at, now that you have like another threshold, you have 4 Riemann sheets instead of 2. And then all the poles are situated. When I say all the poles, it's because we generate a lot of pseudo data according to this data. It's called a bootstrap. So we have like the distribution of all the poles that are here. And if those guys, they go toward the physical sheet, it's a real bound state, like a real particle. If they go toward the unphysical sheet here, it's a virtual state. When I say this movement is when we decouple the gypsy proton case. So what's happening here is that we see that they all go to the unphysical sheet. So that means that this guy here, according to this analysis, which is the very general, it's not a real particle. It's not like the deuteron. It's like a virtual state, right? So that's why I explained that before. It's because this guy appeared to be a virtual state. So you can always say, yeah, but it was based on model, amplitudes, and some model, some parametrization. So we try to go beyond that, and we try to do the same analysis, but not with some models that we wrote by hand, but by using like a neural network, just like even more agnostic about the parameterization that you can write on a piece of paper. So we did the same analysis, and then the result was the same, is that a virtual pole, so V means virtual, B means bound state. There were 4 cases because it can be on sheet 2, sheet 4, but basically it's a virtual state. So this analysis with a neural network confirmed what we've been doing before. So these are also data that, yeah, I can skip that. So you heard about, bound state, virtual state in potential scattering. I'm sure most of you are very curious about that and want to know more. We are giving introductory seminar every Thursday. We started last week. There were 50 people connected, students, master students, PhD students, colleagues. There were even around 5 ICCUB members connected. So we go from every Thursday from now to May. Everybody is welcome to join. We do that by Zoom. And then, so just to, well, I think I ran out of time, but just to conclude, I show you how to analyze data just to understand how resonances of bound state can emerge from interaction of elementary particles. So thank you for your attention.
Vincent. Thank you. So there is time for some questions.
Thank you for this nice talk. So, end of the story of the pi 1.
Yes.
So, what kind of
so here we're certain. So we're certain that it's not a QQ bar because it's a P wave. So it cannot be a QQ bar. Now, it's true that this kind of analysis doesn't tell you if it's like a QQ bar with an excited state or if it's like a tetraquark, right? So, but we do have extracted like the pole, so the pole position. And now you can compare that with some theoretical analysis based on QCD. If the mass, the width, its property matches with more like a QQ bar and an excited field interpretation. So this is the missing link, if you want, that I didn't present it. So everything points into that direction, but because if it was like a 4 quarks, it would be much heavier, right? So this is, yeah, I skipped that somehow.
Okay, there is time for another question.
Yeah, thank you. So, thank you. You started the talk very nicely describing, the basic where we are with quarks and so on. But then I did not really get what is your ultimate goal in analyzing all these resonances and Hadron spectroscopy? What are you after?
So here we would like to understand what are the degrees of freedom that really plays a role. So we know that in the nuclear matter, so we have pions, protons, but then for instance we don't know if other tetraquark or pentaquark, they do play a role. That means that when we describe the nuclear matter in more complicated systems, like in number, do we need to consider those resonances, right? So in the nuclear matter, we know that the delta play a big role, like the delta that I presented here, right? In the beginning. So this one, yes, the delta. So this one certainly do play a role. I mean, you need to consider that when you look at some nuclear matter, right? So the question we try to answer is whether there are other type of configuration of quark that you need. So of course, before trying to understand bigger reaction when you have several protons and pions, we need to understand first if this little signal that we see, like the pentaquark, I mean, the pentaquark have been seen as very specific decay, But is it like a universal resonance, or is it just like a virtual state that we see that we can, yes, it does create some enhancement, it does explain the data in that particular decay, but it's totally irrelevant for other reactions. So we can just ignore this. So that's the type of question. So do we need to consider those exotic resonances in the more general nuclear matter?
Okay, so Vincent, thank you very much again for your nice talk.
Thanks. Esto está aquí. Ah, sí. Sí, sí.